You hopefully learned a lot about redox in your chemistry classes, so today will hopefully mostly be a review of that, but also a big picture look at where redox occurs in biochemistry and why redox occurs in biochemistry, how we can use the passing of electrons from things that don't want it that much to something that wants it a lot, oxygen, in order to get energy and drive reactions like the production of ATP. We'll look at how this is basically going to be transferred by molecules like NAD+, where that electrons are actually going and how you can tell if something's being oxidized or reduced. Let's look at all of that. A quick review of redox, and then we'll look at some examples. I like to remember it as oil rig. Oxidation is loss of electrons and reduction is gain of electrons. Another way that some people like to remember this is with the mnemonic Leo the lion says grr. And so this would be loss of electrons is oxidation and gain of electrons is reduction. Maybe they do it with an E, I don't know. I've always used oil rig. But those are two mnemonics you can use to remember this. Instead of thinking about oxidation as loss of electrons or reduction as gain of electrons, I like to think of it as oxidation is loss of electron density and reduction is gain of electron density. Because in biochemistry, instead of seeing whole electrons kind of move around, what we're usually seeing is changes in electron density, or basically where shared electrons like to hang out. So if you think about a bond, so you have two atoms and they're joined in a covalent bond. If you have a non-polar covalent bond, you're going to get something like this, where the atoms are kind of going to share this equally. But if you have something where one is more electronegative, well, now the shared electron density can kind of shift towards the one. And so that would be a polar covalent bond. Because remember, in a covalent bond, you have their electron clouds kind of merging, and the electrons are moving around all randomly throughout this cloud, but they're more likely to be found near the more electronegative one. And so you get this shift towards the more electronegative atom. And if you were to go from some situation like this to some situation like this, well, this atom, it's going to get more of the electron density, so it's going to be reduced. And this atom, it's going to have electron density pulled away from it, so it's going to be oxidized. To put this a little more concretely, if shared electrons are pulled away, an atom has been oxidized. And why would electrons be pulled away? Well, they get pulled away if they bind to or form more bonds to something that is electronegative. And if we think about our friends in electronegativity, if we remember our periodic trends, we have something like that on our periodic table, where we're going to have the more electronegative things are going to be up on the upper right. And so if one of the main ones we're going to be dealing with that's electronegative is going to be our oxygen. So oxygen is going to kind of almost always win the battle. And if we think about things at the lower end, we're going to have our hydrogen. And so hydrogen is always often going to lose the battle. So typically, if you form a bond to oxygen, or if you form more bonds to oxygen, you're going to have electrons pulled away. So this is why oxidation is often, but not always, associated with oxidation. Conversely, if you're bonding to a hydrogen, well, hydrogen is pretty much like a free electron because it can't hold on to its electrons very tightly. So you get to pull more of it. And so if something is bond to switches a bond from like an oxygen to a bond to a hydrogen, well, now it's going to be reduced. So reduction is often, but not always, associated with bonds to hydrogen. But as we'll see, we need to be careful because we're talking about hydrogen here with its electron and not just hydrogen as a proton. So we'll take a look at how protonation is not a redox reaction, and we'll put some actual numbers to it. But first, always remember that oxidation and reduction are going to go together. So that thing that gains electron density, the thing that gets reduced, it had to oxidize something in order to do so. So we refer to it as like in its like active form or whatever. So we refer to it as an oxidant or an oxidizing agent because it's oxidizing something else. That something else is losing electrons. So this is gaining electrons. And so the thing that gets reduced is the oxidizing agent. And the thing that gets oxidized, the thing that is losing electrons, well, it had to reduce something to do so. It had to give those electrons to something. So it's called a reductant or a reducing agent. And so some common reducing agents that you'll see in the lab and in your body, some of these. In our body, what we're going to see is glutathione a lot. This is going to use sulfur, and we'll look at a little bit about that and the oxidation states of sulfur later. And what we're also going to see in the lab, so that'd be body. In the lab, a couple of the things you're going to see are DTT, thiothriotol, and beta mercaptoethanol. So that's your BME. And you might see TSEP. So those are some of the common reducing agents that you'll see in the lab, as well as in your body. Okay, let's get a little formal and see how we can formally determine the oxidation number. And this is going to be a way where even if you can't intuitively look and see whether something has been oxidized or reduced, you can figure it out mathematically. What you have to do to determine the oxidation number is find the valence number of the neutral form of the element, subtract how many electrons that atom would own if its bond were ionic. We'll get more into this in a second, and that will give you the oxidation number. And to determine how many electrons it would own if the bond were ionic, you have to look and see what's more electronegative. The more electronegative atom wins. So remember we said that oxygen is going to be pretty much the most electronegative one we're going to talk about, and then hydrogen is going to be the least. So what would happen, so the reason why I have these like poker chips, we'll see this in a minute, how this is one of the analogies that you can use in order to kind of think about this. But first I want to think back in terms of my electrons as dogs analogy, where our electrons are energetic dogs, and they're being walked by the protons that are kind of pulling the electrons in using their positive charge as pulling power. We can think about if we have a bond, this would be kind of like the two dog walkers hanging out together, where each of them is holding on to a certain number of dogs, and some of those dogs are going to be shared. What would happen if the dog walkers split? Well, the shared dogs would have to decide who they would want to go with. Would they want to go with walker 1, or would they want to go with walker 2? Now, if you had a fully covalent bond, the sharing would be very even. The only time you would get like a truly fully covalent bond is when you have the atoms of same elements. Atoms of the same element are going to give you these fully covalent bonds. When you have one of these, then it's kind of like 50-50 which the dog would want to go with. Who would the electron want to go with? Well, they're both equal. And so if you were to split these up, each one would get to keep one electron. So in order to determine the oxidation number, we're going to say, okay, if we split these, who would get to keep custody of the electrons, and what would the owner's charge be? Don't worry, this is just a hypothetical split. For now, they're still in love. But let's go ahead and split them theoretically and think about where the electrons would end up. In each of these cases, we have these hydrogens that have equal pulling power. So we have our two hydrogens, and each of them would kind of have equal power. So you would end up with each one ending up with a single electron in this hypothetical split. So remember, it's not a real split, it's a hypothetical split. And now if we think about how many hydrogens, how many electrons a hydrogen would have in its neutral form. So in neutral form, H has 1 electron. Here, it has 1 electron. And so if we have 1 minus 1 equals 0, we end up with an oxidation state of 0 for each of these. And in fact, that is exactly what we see. So that was a nonpolar covalent bond, but now let's think about a polar covalent bond. So in this case, we're going to have unfair sharing. And so in this case, let's take the example of water, H2O. What would happen if you split this up? Where would the electrons go with? The electrons would want to go hang out with the oxygen because that oxygen is going to be better at wooing those dogs. It has a stronger pull over them. So if we were to split these up, then those electrons would want to hang out with the oxygen. So let's go ahead and sketch out what would happen. We would have our oxygen, and it would get to keep each of the electrons from the bond. I'm only going to draw the outer shell. It would get to keep each of those electrons from the bonds, and then the hydrogens would be left without any electrons. Now, the oxygen, to begin with, it had in its neutral form, it has 6. Now it's going to end up with 8. 6 minus 8 equals -2. So the oxygen has this oxidation state of -2. What about the hydrogen? In its neutral form, it starts with 1. Now it has 0, so it's going to have an oxidation state of +1. And the exact same thing is going to be the case for the other hydrogen. Overall, if we add up our hypothetical charges, if we add up the oxidation numbers, they should equal the formal charge. So sum of the ox numbers should equal the formal charge. So if you start with a neutral molecule, the sum of the oxidation states should be 0. And in fact, if we take +1 plus +1 plus -2, we get 2 minus 2 equals 0. So check. So we can see that our oxygen has an oxidation number of -2 and our hydrogens have oxidations of +1. Now, what about ionic bonds? So when we're talking about oxidation numbers, we're kind of thinking about hypothetical ionic bonds. But what if we're thinking about real ionic bonds? So remember, an ionic bond, it's really more just like a strong attraction because it's an attraction between full charges, full opposite charges. And you get a full opposite charge by having a difference of an electron. In an ionic bond, what happens is one atom gives up an electron, and then the other atom takes it. The one that gave it up is now going to have a plus charge, and the one that takes it is going to have a minus charge. So in the case of our sodium chloride, we have the sodium is going to give up an electron to get the full outer shell, and it's going to give that electron to chlorine. When it gives up that electron, well, now it has one less negative charge, so it has a positive charge because it was neutral. When a neutral chlorine accepts an electron, well, now it's going to have a charge of -1. Now, these are actual charges. These are not just like the hypothetical charges, but when we're calculating those hypothetical charges of oxidation states, we're basically trying to say, okay, if the bond was ionic, what would it be? So if they really were to split apart, what would they be? And here we're saying, yeah, they really are splitting apart. So when you have an ionic bond, this is going to involve atoms with formal charges, not just hypothetical ones. And so we're going to see that our formal charge is also going to be equal to our oxidation number. Because you're going to have how many electrons you started with minus how many electrons you end up with to get the oxidation number. So for chlorine, it started with 7 in its neutral form. Now it has 8, and so it has an oxidation number of -1, as well as a formal charge of -1, because remember, this transfer actually is taking place. With the sodium, it started with 1, it ends up with 0. 1 minus 0 is +1. It has both an oxidation number of +1, as well as a formal charge of +1. So remember, in an ionic bond, you're actually doing that split. And in a just a normal covalent bond, then it's just a hypothetical split. Thinking about, okay, well, what if it was an ionic bond? Okay, so let's go back and let's look at a different analogy, a different way that we can think about this in terms of poker chips. And so the reason why I have these drawn in here before is because what I also like to do is I like to think about these electrons as being kind of like poker chips. And the reason why this analogy makes sense to me is because in biochemistry, we're often dealing with oxidation and reduction in the terms of a metabolism. So when we're breaking down molecules or building up molecules, often we're going to be talking about breaking down molecules to get energy. And the more electrons you start with, the more energy you can end up with, because what's going to happen in metabolism is we're going to be kind of passing electrons off from thing to thing in order to generate at the end, get a big payout of ATP. And we'll talk much, much more about this when we get into metabolism. But this is going just a little context as to why we have this poker analogy. So in this analogy, basically, you want to think about the number of poker chips you have as the number of valence electrons that you have. And so we can go back to our periodic table, and we have things in the first column. These are going to have one valence electron. And remember, this is in its neutral form. When we have carbon, this is going to have 4. Oxygen is going to have 6. We have our nitrogen that's going to have 5. Chlorine has 7. And the same thing happens for the things that are below it on the periodic table down within a group. So you're going to have sulfur is also going to have 6, just like oxygen. Phosphorus is also going to have 5, just like nitrogen. And chlorine is going to have 7, just like fluorine. And with this analogy, then what we can do is we can think about each of these oxidation number determinations as a sort of hand in poker. And if these were to break up, who would win the hand? Remember that what you need to do in order to determine the actual oxidation number is figure out the valence number in the neutral form, subtract how many it would own if the bond were ionic. So if they were to split up, who would the electrons get to stay with? Remembering that the more electronegative atom is going to win. So the one that's more electronegative is going to be able to own the bonds, own the electrons if they were to split. And this is going to give you your oxidation number. So why don't you go ahead and pause the video and try this out for this molecule formic acid. Draw lines showing how the electrons would get divvied up if this were to get broken up, and then determine the formal oxidation numbers for each of the atoms. Okay, let's go ahead and do this. Let's start with this oxygen and the hydrogen. Remember that oxygen is really good at drawing electrons. It's really electronegative, and hydrogen is really bad at it. So if you have a hydrogen-oxygen bond, the oxygen is going to win out. So what we can do is if we were to sketch out how this would go, well, the hydrogen would be left with nothing, and then the oxygen would get to keep these electrons. So in this bond, well, then this hydrogen, it would end up with 0 electrons. It started with 1. Now it has 0. So it's going to have a +1 oxidation state. Now we can't do the oxygen yet because we still have to account for this side, this other bond that it's forming. Now oxygen is still more electronegative than carbon, so it's going to be able to keep these as well. So when we split these up, this oxygen is going to end up with 8 electrons. It started with 6. 6 minus 8 is -2. So this oxygen is going to have an oxidation state of -2. Let's look at this other oxygen. Well, it's got a double bond to carbon. And so if it has a double bond to carbon, well, now there's 4 electrons that are potentially up for grabs. And oxygen is going to grab all of them because oxygen is more electronegative than carbon. So what we're going to end up with is we have still the same as before. We started with 6, and now we have 1, 2, 3, 4, 5, 6, 7, 8. So 6 minus 8 is -2. So once again, we have an oxidation state of -2 for this oxygen. And if you can see, okay, well, the oxygen is forming basically 2 bonds here. to another atom that it gets to take. And here it's forming two bonds, but in the form of a double bond to another atom that it gets to take from. So both having a single double bond as well as having two single bonds is going to get you to a -2 state for oxygen. Let's consider this hydrogen over here. So we think about in terms of polarity, in terms of bonds, we typically think about hydrocarbons as being pretty nonpolar. But in the case of oxidation numbers, we do have that carbon is more electronegative than hydrogen. So if these were to split, the carbon would get to keep things and the hydrogen would be left with nothing. Just like before we saw, we have 1 minus 0 equals a +1 charge for that hydrogen. And now let's look at this carbon. Well, it gets to keep the 2 from this bond, but it lost these ones. And so it started with 4 and now it only has 2. So it's going to have an oxidation state of +2. And now we need to check our work because remember, we want to make sure that the charges add up to 0 because we have a neutral molecule. So check sum. It should equal formal charge. And in this case, we want that to be 0. So if we go ahead, we have our +1, our -2, our -2, our +1, and our +2. So we can write that out, +1, -2, +2, -2, +1. And if we do this, we have -1, +2, +1, -2, -1, +1 equals 0. So basically, or you can think about that. And then let's cancel out that. So we get 0. And so that's what we wanted. So this is going to be valid. And here's just another way of showing that. Okay, so there we're drawing the oxidation numbers for everything. But often we're going to be focusing on the carbon. And so for these examples, go ahead and you can figure out the oxidation numbers for all of them if you want. But I want you to be sure to kind of figure out the oxidation number for carbon, because this is going to be kind of like a core to metabolism is going to be the oxidation of hydrocarbons and oxidizing carbon. So remember that in order to do this, what you're going to need to do is figure out the valence electrons in neutral, and then the owned in bonds if they were to split. And then, so this minus that equals that. And so if we're talking about carbon in each of these cases, I'll give you a hint, and that this valence electron in the neutral form is always going to be 4. Okay, so why don't you go ahead and try this out? Okay, so let's start with methane. Well, if we were to split this bond, basically it would get to take all of these because it's more electronegative than the hydrogens. So what we would have is we would have 4, and it would get to own, it would start with 4. Well, now it's going to get to own 8 because remember there's 2 electrons per bond. And so we would get an oxidation number of -4 for the methane. How about the methanol? Well, it's going to get to keep these ones with the hydrogen, but it's not going to get to keep the one with the oxygen. So what it's going to get is it's going to get to keep 6. So we have 4 minus 6 is -2. We have an oxidation number of -2. How about for our formaldehyde? It's going to get to keep the ones from the hydrogen bond, but it's going to lose the one from the bond to oxygen. So if we start with 4, now we're left with 4, 2 from each of these bonds. And we're going to get an oxidation number of 0. If we think about formic acid, well, here what's happening, we've gained another bond to oxygen. Remember before our intuitive thing about how if we gained a bond to oxygen, that's often going to be an oxidation reaction. Well, let's see, we should then have an increase in our oxidation number. So let's see if this is actually what's going to happen. Well, it's going to get to keep this bond to the hydrogen, but it's going to lose both of these to the electron. So it's going to lose 1, 2, 3, 4, 5, 6, and it's only going to get to keep 2. So we have 4 minus 2 equals +2. And how about with carbon dioxide? Well, here it's going to lose all of these. So we're going to get 4 minus 0 equals plus 4. Okay, so now let's take a look at what's actually happening. If we go from methane to methanol, we're gaining a bond to an oxygen. Remember how before we said that, like intuitively, that gaining a bond to oxygen is typically going to be an oxidation reaction because oxygen is so electronegative? Well, here we're kind of putting numbers to it. We form a bond to oxygen, and now our oxidation number increases by 2. The reason why it's increasing by 2 is because you have 2 bonds in that 2 electrons in that bond that are up for grabs, and the oxygen is going to take both of them. Well, if you go from methanol to formaldehyde, well, now you're forming a second bond to oxygen. You're giving up a bond to hydrogen where you got to keep both of the electrons to a bond to an oxygen where you have to give those up. So in this case, our oxidation number is going to increase by 2 again. What if we go between formaldehyde and formic acid? Well, here again, we're forming a bond to oxygen. We're swapping out a bond to hydrogen where we got to keep the electrons to a bond to oxygen where we have to basically give up those electrons. And so we're going to once again increase our oxidation number by 2. And finally, we see the same thing as we go from formic acid to carbon dioxide. We're going to increase our oxidation number by 2 because we're losing another 2 electrons for that bond. So in terms of what's happening here is we're going to have, as we go in this direction, C is getting oxidized. And that's often going to be associated with a bond to oxygen and or a loss of a bond to hydrogen. Alternatively, instead of going and trying to figure out valence electrons and all of this sort of thing, what you can do is basically just cheat a little. Look at each bond that's being formed and see if the atom is being given more electrons, in which case your oxidation number will be lower, or whether it's losing electrons, in which case the oxidation number would be higher. So for example, in the case of our formic acid, we can look at each of these bonds. We see that in this bond, it's gaining an electron, but in these, we have 1, 2, 3 electrons that are basically being lost. If we're losing 3 electrons, we're gaining 1 electron. This is going to be a net loss of 2 electrons. If you're losing 2 electrons, well, then you're going to have a +2 charge. Alternatively, if we look at something like methanol, well, here, if we look at each of the bonds that's being formed, we can see we have 3 bonds to hydrogen in which we're gaining an electron. This would contribute to a -3. However, we also have a bond to an oxygen, in which case we're losing an electron, so +1. -3 + 1 leaves us with a -2 oxidation state with our carbon. If we look at formaldehyde, well, here we have 2 bonds in which we are gaining an electron, so that'd be -2, but then we have 2 bonds in which we're losing an electron, so that would be a +2. -2 + 2, 0. And with formaldehyde, well, here, again, we have a bond to a hydrogen that's going to gain an electron, so that would be a -1. But then we have 1, 2, 3 bonds in which we're basically bonding to oxygen, so we are going to lose an electron. -1 + 3 leaves us with a +2 oxidation state. So that's another way of kind of figuring out the oxidation state. But you should get the same numbers either way. Hopefully what you can also see too is that we're changing by multiples of 2. We're going from -2 to 0 to +2 in terms of our carbon's oxidation state. This means that what we are doing is we're transferring pairs of electrons. So not just single electrons, but actually pairs of electrons. And so remember that if something is being reduced, well, that's because something else was getting oxidized. And if something was getting oxidized, it was because something else was getting reduced. So basically, if we're oxidizing a carbon, what we're saying is now we are taking electrons away from that carbon, and we're taking a pair of electrons away from the carbon at a time. And so where are these pairs of electrons going to go? Well, they need to go to something that is going to then get reduced. And the typical thing that we do in biochemistry, the place where we can put that pair of electrons, that's going to be our NAD+. or FID. Let's look at a little more detail at this NAD+. First off, the NAD+, the plus doesn't refer to the overall charge of the molecule. In fact, overall, it's going to be negatively charged. The plus, however, refers to the positive charge that's on the nitrogen in this sort of like business end of the NAD+. What's going to happen is that basically this NAD+ is going to accept a hydride. So a hydride, that's just going to be a hydrogen with 2 electrons and a negative charge. So remember that a hydrogen has 1 proton and 1 electron. And well, if you give it another electron, now it's going to have a negative charge. And so this is what we call a hydride. And this is what we're going to transfer onto NAD+. So you can see here that this is what we have. This is going to be our hydride. And so how are we going to get that hydride that we're going to transfer? Basically, what we're going to have is if we start with some sort of carbon that is in the alcohol form, what we can do is we can think about this, this hydrogen as leaving with this pair of electrons. So this hydrogen is leaving as a hydride. So that's going to be our hydrogen with these 2 electrons and this minus charge. That's what's going to be lost. And it's not just going to like fly off. Instead, basically, this oxygen is going to be, the lone pair from this oxygen is going to form a double bond. And then when carbon has, it already had 4 things attached to it, and now you're adding a 5th. So something's got to go, and so that hydride can go. Now this hydride can go and it can add to the NAD. And so basically what you'll have is you'll have this hydride, and what it can do is basically this hydrogen is, we're going to add this here, which is going to push this here, which is going to push this here. And so now basically you're transferring electrons to that nitrogen, to that positively charged nitrogen. And so that's going to be stabilizing. Basically, you're neutralizing out that charge. And as a result, what you're going to be doing is you're reducing this NAD+. You're reducing this NAD+, you've given it electrons, and you have given it a basically a proton, because the net sum of this is going to be a proton and 2 electrons. So this is going to be our hydride. And this is going to be reducing the NAD+ to give us NADH. So the H here is indicating that we've added this hydrogen, but remember, it's not the hydrogen that really matters, it's the pair of electrons. And so this is why we say that this is reducing NAD+. So we reduce NAD+ when we oxidize this. So you can imagine too that basically if you were to carry this out, well, now what you'd actually end up with is you have this awkward state where this carbon is going to then have this, this carbonyl is going to be protonated. And so you can imagine too that this is going to quickly then be lost to solution, because that's not going to be very happy, the oxygen like that. And so you can quickly get these proton transfers to happen and end up with having your carbon in a carbonyl that's not protonated. And so basically you can just think of some sort of base coming in and stealing that proton. What if instead of just some sort of ketone, we actually had an aldehyde? Well, now we have the chance to oxidize it even further to a carboxylic acid. So in our situation like this, what we would have is we would have a hydrogen here. If we lose this hydrogen with the pair of electrons that were in the bond, so if we lose a hydride here, now what we're going to be left with is this weird intermediate that's never really going to exist, because basically we would have this super unstable carbocation. You can imagine that if you had a water molecule, that oxygen would happily add right onto here. And then after you get that protonate. Basically what you're going to end up with is then you're going to have this. And this is why you did then this. We basically still had a pair of electrons being transferred here, and that pair of electrons could get transferred on to NAD+. So this is why actually what you'll often see is you're going to see NAD+ and NADH plus H plus, because basically you're going to have lost the proton here, or have lost the proton from the water here. And remember, these proton transfers are going to be really, really fast. And so what we're going to get is then be having a proton be released. And so this is why you'll often see it written this way. But ultimately, what is the key thing that is going to be happening is that we get this transfer of the hydride. So we have the proton and our 2 electrons. That's what's really key, is what's being transferred there. And then this protein, the other proton, is just kind of like to balance things out. But remember, we're having this hydrogen basically leave with the electrons that it was in the bond with. And so it's getting 2 electrons. It's getting both the electrons from this bond, and those electrons have to go somewhere, and they're often going to NAD+. This is why we have this NAD+ be so great, because it can accept a pair of electrons. When it accepts a pair of electrons along with the hydrogen, so along with that proton, well, now we get NADH. The H is indicating that we have this hydrogen be added. The plus was indicating that this nitrogen was positively charged before. And overall, though, the really key thing is that you're actually transferring those electrons. And later, NAD+, or NADH, is able to then go take those electrons into the mitochondria, into the electron transport chain, and there it can be used to cache off those electrons. Because when you pass electrons from something that has a lower reducing potential to a higher reducing potential, you give the electrons to something that wants it more. Well, when you do that, now what's going to happen is that you're going to have a negative delta G. And so if we give electrons from NADH to various transport molecules, if we then add it to oxygen, well, now we're basically getting this really, really large drive of energy that's going to power the synthesis of ATP. Remember, we said that it was going to be really hard to synthesize ATP, but by using the flow of electrons, we're able to pump protons out of the mitochondrial matrix. To do this, we're creating this large electrochemical gradient that's then going to flow through this pump and give us, so that we can take ADP, we can take inorganic phosphate, combine them to make ATP. And we're able to do this thanks to the fact that the oxygen is such a great reducing potential. It really, really wants those electrons. And so our job with like glycolysis, with other catabolic pathways, is we want to transfer those electrons from things that don't want them as much to something that wants them more. As we do so, we're releasing little bits of energy. We've got that negative delta G, until ultimately we're passing things on to oxygen, which wants it the most. And this is going to allow us to power the synthesis of ATP. And now let's look at another type of problem, or it's the same type of problem, but it's something that comes up often in biochemistry, and I don't want you to get confused about, and I want you to have an intuitive sense of. So I want you to calculate the oxidation numbers for these 2 molecules, formic acid and formate. Well, we already did formic acid, but it's always good to do it again. And now let's also do formate. So this is going to be the deprotonated state of the formic acid. I want you to figure out the oxidation numbers. For this one, let's do it for all of the atoms. And then tell me, is redox occurring in order to go between these? So why don't you pause the video and try this out? Okay, so let's go ahead and think about how we split up formic acid. Remember that oxygen is going to get to keep the electrons in the bonds. And for any time when we're talking about a bond that is not nonpolar. And remember, by nonpolar, I'm talking about fully nonpolar. So between like it would have to be between two oxygens. In that case, each one would get one electron, but in all other cases, you're going to have it get 2 electrons from a single bond and 4 from a double bond. So this oxygen is going to be able to take all of them from this bond, and it's going to be able to take all of them from this bond. In terms of a carbon-hydrogen bond, well, here we have the carbon is going to get to keep these electrons. So if we start with the hydrogens, well, in this case, it lost electrons in both of those cases. It started with 1, and now it has 0, so it has an oxidation state of +1. Same with this hydrogen. It started with 1, it ends up with 0, it has an oxidation state of +1. If we think about this oxygen, it started with 6, and now what it's going to end up with is we have to remember it has these lone pairs, so it has these 2 lone pairs, so that'd be 4, and then 5, 6, 7, 8. We end up with a -2 charge. For this oxygen, remember, it too has lone pairs. It's going to start with 6. Now it has those 4 from the lone pairs, 4 from this bond. So it has 8, and that gives you an oxidation number of -2. And finally, for this carbon, what we had was we started with 4, and now it ends up with only 2 because it got those ones stolen from the oxygen, but it gets the ones from the hydrogen. So it's going to have a state of +2. And if we do our math, then we can find, okay, -2, that'd be -4. And then we have +4. So this is going to equal 0, and that's going to be correct because this is neutral. Now let's think about formate. So in this case, this oxygen is the same situation. We'd still have a -2. What about this carbon? It's in the same situation, so it's still going to have a +2. This hydrogen, it's in the same situation. It's going to have a +1. And the only thing that really changed is going to be this oxygen over here, which no longer has a bond to hydrogen. Since it no longer has a bond to hydrogen, but it lost the hydrogen as a proton, what that means is that it's going to have 3 lone pairs. If it has 3 lone pairs, so that counts for 6 electrons, and then it still gets these 2 from oxygen, and that's going to be 8. So we have 6 minus 8 equals -2, which is the exact same as it was here. And because the reason is that in the hypothetical split, oxygen would get to keep the electrons from the hydrogen. And so in the actual split, it also gets to keep the bonds or keeps the electrons. So it's not going to change its oxidation state if it's just losing a proton, because it kind of was owning those protons, electrons, anyway, those protons, that hydrogen's electrons in the first place. So what we have is that protonation, deprotonation is not redox. So when we talk about like forming bonds to hydrogen, that is not what we're talking about with forming bonds to protons, because when you basically have a proton, remember that has no electrons. A proton is just a proton, no electrons. And so when we're talking about oxidation and reduction, we're talking about electrons. A proton has no electrons by definition, and so therefore it is not redox. And so don't let this confuse you. If you gain a bond to a hydrogen, we often think about that as being a reduction reaction, but that's because you're gaining a bond to a hydrogen as opposed to something like a bond to an oxygen. So basically you're going from something where you're getting your electrons stolen to something where you get to keep the electrons. So this is why we often have this reduction involving a gain of a bond to hydrogen. But remember there, we're talking about a hydrogen and not a proton. And if we have a loss of a bond to hydrogen, what we think about that as oxidation, but it's because with the hydrogen, we kind of got like a free electron. But if we are then losing that bond to the hydrogen, we're losing that free electron. Whereas if we're just losing a proton, well, now we're keeping that electron. So don't get confused with protonation and deprotonation and redox. So if you want to go back to our dog analogy, basically you could think about that if you were to have deprotonation, it's kind of like the dog staying and the dog walker leaving. Whereas if you had oxidation, what would actually happen was that the hydrogen would have to leave with the dog walker, or you would have to basically switch to a dog walker that is better at wooing you. So an oxygen would have to go from, say, having a bond to a hydrogen, which it can keep the electrons if they were to split, to having a bond to another oxygen where it would have to share them fairly. One other place where you're going to see oxidation and reduction show up in biochemistry is in the case of cysteine and thiols and thiolates and things like this. With cysteine, we're going to see that we can have it be deprotonated or protonated. So we can go from a thiol, the protonated state, to a thiolate, the deprotonated state. And we can also get it oxidized or reduced. So when we say that's in the case of cysteine, when it oxidizes, it forms these like crosslinks. We call these cysteine. And basically, these are disulfur crosslinks, disulfur bonds. Glutathione is an example of a molecule with one of these thiol groups that can form these disulfide bonds and act as an antioxidant. So this form of cysteine, this form of a thiol, when they react like this, when you get a disulfide bond, this is going to be an oxidized form of sulfur compared to the thiol or the thiolate. To help show this, why don't you go ahead and calculate the formal oxidation numbers of sulfur in each of these cases and see where redox is or isn't occurring. So if we think about sulfur, it's right under oxygen on the periodic table. So in neutral form, sulfur has 6 valence electrons. So in this case, it would start with 6, and now let's see what would happen in this bond if it were to split. Well, it gets to keep a bond to hydrogen, and it's also more electronegative than a carbon. And so what it's going to do is it's going to get and keep these bonds as well. And so it's going to have, and it's going to have 2 lone pairs. So we have 1, 2, 3, 4, 5, 6, 7, 8. 6 minus 8 is minus 2. What about in our thiolate? Well, here, remember, we have a deprotonation, and we just talked about how deprotonation is not going to affect the oxidation number or the oxidation state, but now let's show it mathematically. In this case, if we have that negative charge, what that means is that that proton left, but it left behind its electron. So we have these 3 lone pairs, and it's going to keep these electrons from this bond to the carbon. So it gets 2 electrons plus 6 from the lone pairs. 6 minus 8 is minus 2. So here we do not, so this is not redox going this direction. But what about if we go from a sulfur hanging out in a thiol or a thiolate to a sulfur hanging out in a bond to another sulfur? Well, in this case, what we have is one of those so what we have here is that this would be a fully nonpolar covalent because it's involving bonds between the same atom, between atoms of the same element. So it's going to be a fair split. So it's going to get 1 from each of these bonds as well as 2 from each of these. And then again, what we're going to have is here, we're going to have 2 lone pairs. So for each of these, we'd have 1, 2, 3, 4, 5, 6, 7. So we start with 6 minus 7 is a minus 1. And then here we'd have 1, 2, 3, 4, 5, 6, 7. 6 minus 7 equals minus 1. So each of these would have a minus 1. And note that we have minus charges here, but if we were to calculate the oxidation numbers for the rest of the molecule, what we would see is that they should end up equaling out to the charge. So they should end up equaling 0. But the reason why we're not seeing that now is because we've only calculated for the single atoms. Whereas for the oxidation number, the sum, it has to be for the entire molecule. But here you can see that if you go from a thiol or a thiolate to a disulfide bond, what you have is you have an increase in the oxidation number. So if we have an increase in our oxidation number, that's going to be an oxidation. And if we have a decrease in our ox number, that's going to be a reduction. So we can see that in terms of the sulfur, if we go from this state to this state, if we go from a -2 down to up to a -1, that's going to be an increase. That's going to be an oxidation reaction. And if we go the other direction, we're going from a -1 to a -2. That's going to be a reduction reaction. And this is in terms of the sulfur. So if you think about the carbon, well, here is going to be the opposite. So this carbon here, if the sulfur is getting oxidized, then the carbon is getting reduced. It's losing those electrons. So if I ask about like is an atom being oxidized or reduced, I would be talking about a specific atom or each of the atoms individually if you had to figure out the oxidation numbers for each of the atoms. So often we're focusing on the carbon, but there are cases like this where we're going to be focusing on things like the sulfur. So to review what you should be reviewing, recognize when redox is occurring, identify what's being oxidized and what's being reduced, and determine the oxidation numbers. So remember, to find oxidation number, what you want to do is determine number of valence electrons in neutral form, subtract how many it would own in split. And remember that the more electronegative atom wins. And this is going to give you your oxidation number. And then remember that increase in ox number equals oxidation. Decrease in ox number equals reduction. And this is in terms of an individual atom within a molecule. Also remember that deprotonation and protonation are not redox. But you will often see that a bond increase of bonds to oxygen is going to be an oxidation. Because oxygen is so electronegative, it's kind of always going to steal those electrons, so you're going to lose them. And the gain of a bond to hydrogen, well, that's almost always going to be a reduction reaction, because you kind of get those electrons for free if you get them if you form a bond to a hydrogen. But that's a bond to a hydrogen with its electrons and not just a proton. Remember, by definition, a proton does not have an electron. And by definition, redox involves electrons. And what we'll see in biochemistry is that typically catabolic reactions, so when we're breaking down molecules for energy, these are typically going to involve oxidation reactions, and anabolic reactions where we're building up molecules. These are going to be more of our reductions in terms of our carbon. And we'll get much, much more into that. Metabolism is a key place where you're going to see this redox show up.